you. Good morning, everyone. Hope you've still got some energy. Hi, my name's Alison Quinn. I am a Senior Analytics Specialist Solution Architect here at AWS. I work with our financial services customers across the region, and I have one of my customers here today, Subas, and I cannot wait to share with you the journey that his team has been on and what they have built. We're going to cover a lot today. If you don't have perfect 20/20 vision, my recommendation is that you move to the front. There's going to be a lot of really detailed architecture diagrams that Subas is going to run through. Remember, this session is being live streamed and recorded, so at any time you can go back and catch up and have another look at us again. I'm going to go through a high-level architecture. Subas is going to go through the details of the architecture, and then I'm going to talk to the summary of their success. So, to start off with, anyone in the room that can identify with this picture? Getting data from A to B, it's not always as simple as just like a line, right? It's not really sometimes that easy. We've probably got a lot of people in the room that can relate to that. These are some of the challenges that I see common across my customers when it comes to data pipelines and data management. Okay, so everything from complexity of build, latency of landing and transforming that data, through to the scalability issues. Some of these are probably familiar to some of you in the room. Now what I'm going to do is going to talk to some very specific challenges that the NAB solution meets. Increasing scope. Anyone ever had some increasing scope? I'm seeing some smiles in the room. Subas and his team first started off with around 100 interfaces into their system. A few months later, they're now dealing with over 700. You can learn how they've done that. Loading dependencies. When I load A, can I load B straight away? Do I have to wait for A to have completed? Those kind of dependencies, and they can get really complicated. Subas is going to talk to how they've resolved that. Next one, data duplication. Have we ever had the same data come to us more than once? I'm seeing some nods in the room too. We'll learn how Subas and the team have dealt with that one. Data quality. I'm sure everyone in the room has at some point dealt with a data quality issue. If not, perhaps you're in the wrong room. We're going to hear about how that has been dealt with, making sure we have the right data types, our primary keys are there, etc. And finally, error handling. Isn't it nice to know when something's gone wrong before your business end user knows that's gone wrong? Let's hear about how they've dealt with that. I'm sure you're all thinking about all the challenges you've had and you have in your current environment, and you can't wait to hear how the team has resolved it. This is the 1,000-mile architectural view. These are the key AWS services that have been used in this solution. From an orchestration perspective, we see event-driven, scalable, and serverless solutions that have been used. We'll hear Subas talk a lot about the use of AWS step functions and state machines in the solution. Metadata drives everything in this solution, and the NAB solution designers and analysts alike are able to add additional data ingestions or transformations through this metadata. This metadata is all stored in Redshift, as are the outputs. And finally, the team wanted to build for tomorrow and on a code-generated base, a common framework. So you're going to see examples of code-generated for dbt macros, code-generated for SQL Redshift, code-generated for the state machine step functions, and glue jobs. With no further ado, I'm going to hand over to Subas, get him to introduce himself, and he's going to start going through the detail of this architecture.
Thanks, Ali. So, hi, I'm Subas, and I'm a senior consulting engineer at NAB. So when we started our journey to build this framework, and very early on, we realized one thing that sort of the biggest bottleneck for us is the complex dependency between the pipelines. So you have fragments of pipelines. You need to load a table. You can only load it if, say for example, the source file of that is available, maybe a control file on which it depends on. You need to ask the question, have I loaded it already today? Some cases it will have a downstream dependency. For example, if you're generating data and sending to another system, maybe they accept the data only on the, say, working days and non-holidays. So as those dependencies started getting more and more complex for us, we realized that a centralized solution requires a lot of impact analysis every time we try to make a modification there. And we need to distribute that. And second problem was maintaining the infrastructure. We wanted to go serverless so that we can seamlessly scale till infinity. That's where we came out with the idea of an observer. So the idea of an observer is that everything in our system is even. When a file arrives, it becomes an event. When a table gets loaded, it becomes another event. If there is a data quality failure, even within, while loading a table, it becomes an event. And observer essentially, he takes those events. So essentially, even during the design time itself, we specify what all events an observer depends on. We call them observables. And it takes, say, one or more conditions, which is a Boolean formula on top of those conditions. And once that formula evaluates to true, then there are a set of actions that we can associate with the observer. Say, for example, it can then ingest a file, it can transform a table, and so on. So without much ado, what we do is with every table or every fragment of pipeline, we associate one observer. And at the design time itself, we can analyze those dependencies and create a lineage graph. We can identify if there is a circular dependency between that we have created. But what it allows us is that every solution designer can define those dependencies for every individual fragment of pipeline, and that allows us to scale faster because they can parallelly and independently start defining those dependencies, and at the design time itself we can verify those. Not only that, we also need to evaluate those conditions, as I mentioned. So we use, again, Lambda as a service for that. So everything in our system is an event, as I mentioned, and those are stored in our Redshift tables. Lambda could go and query those events and then evaluate whether a dependent set of event is true for a particular pipeline. And if it is true, then Lambda returns back saying, okay, it's true. You can go and perform whatever set of actions that is associated with it. So without, what I'll do is I'll possibly go through the design time, how we build these observers. So at the design time, we start with a set of APIs. So we have defined set of Python APIs. So through which one defines, say for example, what are the SLAs associated with a observer, what is the file pattern that it is going to look for. Then we define set of observable that it is dependent on. And then we combine those different observables as a Boolean condition. And I'll show you how that Boolean conditions are defined. Once these Python codes are defined, in many cases we also auto-generate them through our metadata. And once this is generated, the first thing that happens is across all these different observer that our developers or solution engineers have defined, we generate a lineage graph, and then our CI/CD pipeline deploys that as a table in the Redshift, which we'll see how it is queried at the runtime. Then for every observer, we also generate a JSON, which is nothing but the observer defined as a state machine. That also gets deployed through our CI/CD pipeline in our environment. So, and then that manifests itself as one of the observer associated with each and every fragments of the pipeline.
Okay, so what I'm hearing is the first two challenges are coming up. One, scale, so you're generating a new state machine for every ingested file. And I'm also hearing around the dependencies challenge. So that lineage DAG that is stored and keeps all the details of the dependencies, I'm hearing all about that. Okay,
Right.
now we're going to go through an example, right?
Right, yeah. So let's go through an example so that it becomes clear. Assume that a file arrives, and let's go through the journey of an observer. So file arrives, as you can see, the moment a file arrives, we have triggers on our S3 buckets. So that creates an SNS, SQS, and it triggers a Lambda. We call that Lambda a state updater Lambda. And what we have done is we have written grammar for every file pattern. We have done it in Antler. So at the bottom, you can see an example for this particular file. We can extract out information from the file name itself. Like we can extract out what is the load date associated with it, what is the unique dataset name associated with it, what is the run ID if there are multiple runs of this file. Once these informations are extracted, the state updater Lambda goes and queries the lineage table. Because lineage table has the information that how this unique dataset maps to a particular observer. So once it finds out which observer to start, it takes those additional parameters, that is today's load date, today's run ID, and passes those information to the observer and starts this particular observer. In this case, it's the account file observer that it starts and passes those information. Once the observer starts, observer has two mega state, what we call as the observe state and the action state. In observe state, you can have further business logics. For example, you may have a day zero load or what you call as a history load. You may have a business as usual load. Or even in the development time, you can, say for example, remove all the dependencies and just run the pipeline every time you trigger it. So we can encode those dependencies as conditions. And these are choice state, if you are familiar with these state machines. So those choice states are evaluated based on those different conditions, and then it calls another Lambda. Let's just see what happens in the whole life cycle of the observer. What happens is, as you have seen, the state updater Lambda triggers the state machine, and then it goes through the different conditions, and you can see a condition which we have named as business as usual condition at the bottom. It depends on two different files, the actual file that needs to be loaded, and also the control file that is associated with it. We also checking whether the table has been loaded today already or not, and we are checking whether the whole batch has been successfully completed yesterday or not. The idea is you can associate any arbitrary set of conditions as long as those observables are available within our system, and you can express them as a Boolean formula. That is condition A equal to true, condition B equal to true, and so on. Like you're flexible to define and or not, etc. And many of these conditions are auto-generated within our system from the metadata. Now, once the observer evaluates to true, it goes to the action state. And in action state, it can run, say for example, an ingestion. We'll see example of ingestions and transformation very soon.
Okay, so we've just heard the duplication challenge. We've heard how that passing of the file name and the lineage DAG helps us to understand what has already been done and therefore avoiding duplication in our environment. Now, I have a question for you, Sebas, that I'm sure a lot of people in the audience are thinking. You talk a lot about step functions. Can I ask you, why step functions? Why not, for instance, Airflow that's already used within the bank?
Right, as I was mentioning, like having a centralized decision maker is always a problem, because every time we make a change, we need to go through all the decisions that we have already encoded in it, understand it, and then it becomes difficult for human being to handle 7 plus minus 2. I mean, that's an old research paper I'm citing. But essentially, it becomes difficult unless we distribute it, and we can verify everything automatically at the design time. So that was the idea.
Perfect.
So going forward, let's understand. Say for example, file has arrived. The condition has evaluated to true. So all the dependencies are met. So how does it flow through? Um, in our whole system, everything is defined in terms of the metadata. So our metadata are defined in an Excel sheet. We'll come back to that. So solution designers define the table details, what type of load it is, whether it is a delta load or full load, whether the file has header or trailer, and also column level details, including the data quality checks. Within our code generation pipeline, those information are then picked up and then deployed in the CI/CD pipeline to our S3 bucket. We'll see how those information are then picked up at the runtime. So what happens in the code generation pipeline is, first of all, job may have a complex DAG kind of structure. It may go through multiple stages, like file may come encrypted, you have to unencrypt it, decrypt it, or then deflate it. Then maybe you have to parse the file using the schema information. And then finally, we load it to our Redshift. What I do is, all the assets are derived from the metadata, and everything is auto-generated and then deployed on the S3 bucket.
So I've heard you start to mention data quality, and I know you're going to go a lot deeper into exactly how you do the data quality, but you've mentioned that coming through from the details in the metadata is what you're basing those quality rules on, and you've mentioned Excel, and I saw some smiles in the audience. Why Excel? Have you considered another front end for your end users?
Don't we all love Excel as an UI? The truth is, most of our solution designers are familiar with Excel and they prefer to author things in Excel, but what we do is, what we have done is we have developed a serializer and deserializer over the Excel. So we convert everything into JSON and store it in our Git, so that based on the environment, based on the specific solution, we can compare the branch, and the code generator can pick up the right branch and the deploy based on that. So in some sense, Excel is just the UI, and everything else is in the GitHub as a JSON or YAML file. Going forward, now that we have generated all the artifacts at the design time for ingestion, let me explain what happens at the runtime. So you remember that we have got the load date and the run ID from the previous stage, or when Lambda triggered the state machine. The condition got evaluated to true, and it has now come to the action state. So what happens in the action state is we have code generated all the parameters that we need to pass on to the glue, and those are completely resolved at this stage. And where the pipeline definition is as a YAML file, those path on the S3 bucket, the associated scripts, which needs to be executed in order to load the data going through all the stages, the run ID, associated control file, everything is resolved and is passed on to the glue. Now, once glue receives this information, first thing it does is it goes and downloads the pipeline definition as a YAML file, and then it auto generates the whole DAG and starts executing the stages of this DAG. And during that process, say for example, it has to parse the file. It requires the schema information. That moment it downloads the schema information from the S3 bucket, uses that to parse the file. Then when the time comes to execute the SQLs to load the file onto Redshift, it will again download the SQL file and start executing those. Let's go through another example. In this case, I'll take you through the transform, which we essentially use dbt for that. But I'll take you through a very specific example. It's a data quality check that we are doing on a particular column. So again, everything for us is specified through the metadata. In this example, there's a column named code, and then we are specifying the integer range for that to parse. again, we define an antler grammar for parsing those information. It generates a parse tree that during the code generation, it takes the parse tree and generates a YML file. If you are familiar with the DBT, you know that we can configure DBT tests as a YML file for each and every column or table. And we have written macros for that, which macros at the runtime renders into an SQL, and then those SQLs are executed to run the data quality checks. The last part is checking the SLA breach and other stuff, like say for example, did we load the file today? Have we even received it from the other party? So those are edge scenarios, and again we encode those as a observer as well. The structurally is very similar, only thing is it is triggered by the event bridge. So we configure a cron in the event bridge, and then that triggers the SLA checker, and then it goes through the same process, calls the Lambda to evaluate whether things has been good. If it is not, we can auto-generate the incidents, we can log this information, and then can get integrated with Splunk and so on.
Perfect.
That's mostly.
Excellent. So that is the last of the challenges that I promised to talk through, error handling.
Right.
So automatically being told when something's going wrong, not having to find it out by a third party, and maybe even through an incident response. So that's fabulous. Thank you, Subhas. Now, there has been a lot covered in that, and this is a short session and a lot to go through. So remember, the recording will be available. I'm just going to go and start, whoops. There we go. I'm going to just recap on what we've learnt today from the session and how Subhas and his team have addressed these challenges. So increasing scope, I mentioned that they started with 100 interfaces and now are servicing over 700. So how they've done that is through the metadata, right? They can add another entry for a new interface into the metadata. Their solution designers can just add that into an Excel spreadsheet that then is managed via a CI/CD pipeline in the background, and they can easily increase their scope without having to actually build anything new. The loading dependencies, Subhash talked a lot about the lineage DUG that is stored within Redshift. So this is where all the details of what has been loaded, what is dependent, where the status of everything is stored, so that we can ensure that all of that dependencies are executed from a runtime perspective. Data duplication, we heard how the files that are coming in are parsed, and we can recognize whether we've already loaded this data, whether we've received it already, if we're receiving the same file again and again, so as to avoid data duplication within the environment. And from a data quality perspective, we heard a great example of how the data quality rules are being automatically generated based on that metadata. So if in your metadata you're saying this is a primary key, it must exist. A rule is automatically generated to check that. This is of a particular data type. This field we expect particular values. The SQL is automatically generated to run those data quality checks that are then integrated in from an error handling perspective as well. And finally, error handling. So that was the last one we saw. Being very proactive and understanding if something hasn't arrived that should have arrived by a certain time, taking an action and ensuring that that is fed back to the relevant party. Has anyone visited the AWS Skill Builder? Anyone in here used it? Yeah? Okay, when I use AWS Skill Builder, my kids think that I'm playing computer games because that's kind of the look and feel of it a little bit. So get in there, make your children jealous. There's over 600 free online digital courses available for you. Massive thank you to Subhas and his whole team. I know there's certain members of the team in the audience here today for sharing their story and how they've surpassed these common challenges. Please, we're going to be outside the room, just near the couches, if you have any other further questions for us. And also, please fill out the survey for today's session. Thank you so much for coming along, and enjoy the rest of your summit.
Wow, what a session. Thank you so much. Thanks to Alison and Subhas for obviously sharing this presentation with all of you. Please don't forget to rate the session on the Summit app. Feedback's very important. The next session in this room will be at 12:20. See you then. Cheers.